find the domain and range of this function. In this case, this is the exponential function. So this should be interesting. First off, I would like to clear out a certain part about the relationship between the domain of f and the range of f inverse, and vice versa, of course. And so here I've prepared a couple of stuff. If we have a function f which maps values from one set to another set, then its domain is all the possible inputs. So it's all the possible values it can send, so to say. All the values I can put in this function. And then I can figure out what the domain is. So in this case, for example, the domain of f is going to be A, because this is all the possible input, and I'm sending this input into B, to other points in B. So in that case, the domain of f is A. Now, what can we say about the range of A? The range of f. Well, the range of f is all the possible outputs of f. Here I did not make it absolutely clear, I just pointed at the set B, but you can understand it as being mapped to all the points, and this is also true here. But I will remove it because it's ugly. And so if f maps its values to this whole range of points, then the range of f is B, because B is precisely all the possible outputs that this function can give. So if I look at this function and I look at what values it can output for me, I will get those values from B. Exactly those values from B. So I'm not just going to get a subset, so I'm not just going to get these values, for example. No, I'm going to get all of the values if the range of f is B. And by duality, so we know that the function and its inverse are dual in some sense, like good and bad. Like, any two duals, positive and negative. There's even a negative sign, but we don't try to have positive, and so on and so forth. And by this dual notion, you will see that the domain of f inverse is also going to be B, which is the range of f. So the domain of f inverse is actually the range of f. And this will also be true for the domain of f. It will be the range of f inverse. So this is very important to notice. And we can make sense of this just by looking at what what points does f inverse send. So here, f inverse sends all the points from B. And so, by definition, this is the domain of f inverse. But at the same time, it's the range of f, because the values that are being sent back with f inverse are the values being sent in the first place using f. A similar argument works for the range of f inverse. So this is, to clarify this point, if we can find domain of f and the range of f, then the domain and range of f inverses come to us for free. It's very cheap. Like, we don't need to go out and seek what this domain of, let's say, this inverse function is going to be, or what its range is going to be. So I hope this is now cleared out of the way. And then now we would like to find the domain of f and the range of f. Well, as we've discussed, the domain of f is all possible input. So with functions like this, they're actually nice. So you ask yourself questions, one question, not questions, and that is, what values can you not put? What values can we not input? And it turns out that, well, there are none which you cannot input. I mean, you're just taking powers of e to the, just taking powers of e in general. There's no singularity, for example. It's not, there's going to be like 1 over 0, for example, or anything of the sort. So it's nice in that sense. So that's good. There are no singularities, there are no discontinuities. It's a nice function, it's a smooth function. So in this case, the domain of f is actually going to be all possible values. So all finite negative values and all finite positive values. This is denoted by an open bracket from -infinity to infinity, which means it does not include these limits. Now, as for the range, we need to know a certain fact. And this fact precisely is, okay, maybe that's a big fact. Okay, now it's nicer, now it's smaller. This fact is that e is a positive value. And so effectively here, what we're doing is we're taking powers of a positive number. In principle, taking a power of a number is multiplying it by itself. Yes, I know that e to the 0.5 is not really taking e times itself half a time. It doesn't really make, it doesn't obey our normal intuition, but it is still consistent with what we understand. This is a positive number, and when we multiply a positive number by a positive number, we get a positive number. So that is always true. And for that case, we will always get that the graph of e to the x, and similarly e to the minus x, will be positive. So no values will be less than 0. So e to the x is always greater than 0. When does it really get close to 0? This happens when you get very close to minus infinity, when you take the limit precisely. And we've discussed this we'll discuss this for the next week. But this is what you need to know for now. So as we get very small values of say 0.000000001, the value of e to the x gets smaller, but it never goes below 0. Because if you're multiplying a positive number by itself, then it should always be positive. By the way, I know that this is the graph of e to the x, and it's not the graph of e to the minus x. But if you're wondering, this is the graph of e to the minus x. It's like a mirror. It's very nice. Inverse functions are okay, are nice. And in that case, the range of f would be going from 0, but it does not include 0. It's asymptotically equal to 0, which means it always gets close to 0 but never reaches it. And it includes all the positive values. Now remember, by the range we mean the values for the y-axis. So this is the part of the y-axis that's being covered. And for the x-axis, we're actually covering all of it. So this is the x-axis, and we are able to cover all of this space. This is it.